Thanks, Aaron. I'm glad to be here, and I'm thankful to you folks for your hospitality and fine weather. Hope we all have some rain. I need rain at home, and it sounds like you folks need some rain here as well. So I wanted to use this opportunity to come out and do a couple of things. And I'll talk about the real reason that I'm here a little bit later. But if you pick up the Science Highlights brochure, you'll get an idea of some things that are really important that I didn't get to talk about. I just didn't want to go too long, but I really wanted to talk about my favorite kind of perspective. And so I always use the school bus because Hubble's about the size of a school bus. School buses are associated with new adventures, excitement, most of the things that we remember fondly from our childhoods, I hope. And so I like to use the school bus because there's so much that this incredible instrument has allowed us to discover. And lastly, the school bus represents, for me, a reminder that I'm living my childhood dream. And so tonight I will talk to you a little bit about how I see the dream unfolding each day. Let's see. So the history of astronomy is one that goes back thousands of years as man has recorded what he's seen looking in the sky. It's been limited for most of human history by the human eye being the detector and all of the facilities available. And so we could see what's called about an arc minute of space. This is the size of objects that we can see with our naked eye. And a star in the sky is about right at that arc minute size. And so with Galileo's use of this sight glass, this telescope, was the first instrument that we had really to improve on that a few hundred years ago. And then shortly after that, Isaac Newton came up with a way to implement this reflecting telescope. But it took a long time, 100 years plus, actually into the 1800s before we could effectively use reflecting telescopes. So Banneker and Galileo and all these people had centuries of making observations with a refracting telescope and dealing with the effects of the atmosphere blocking their view of the world. But now we have the Hubble Space Telescope. And if you take this sight of the eye and divide it by 60, you get an arc second in size. It's a fraction of a star or significant features on one of our planets. And Hubble has the ability to see a half arc second, 0.05 arc seconds in the visual spectrum, and in the ultraviolet spectrum, it could improve on that, but in the infrared spectrum, it sees a little bit less clearly. And so this is going to become important as we move through the evening. So this arc second angular resolution of the Hubble Space Telescope and these new ground-based telescopes is really important to the way that the incredible time machine works. But before I do that, I always like to talk to audiences about news that is important that you think you already know. And so I suspect that most of you here have heard that Voyager has left the solar system. Is that correct? Okay. So let me burst your bubble. Voyager has only burst the bubble of the heliopause. And that is this bubble created by the sun pushing on the interstellar winds that are blowing against us, and Voyager has left the area that is principally the domain of our sun's radiation, and it is now experiencing the radiation of the rest of our galaxy, and that's called the heliopause. And so that transition point is still inside of our solar system, and so it's 13 plus billion years away from the Earth, and Voyager 2 is about 10 billion miles, I said years, didn't I? 10 billion miles away from the Earth. So they are really quite far, the farthest any human-made instrument has ever traveled, and their photographs have been the farthest photographs ever taken of our planet, all from Voyager. We hope that Voyager will continue to communicate with us into 2025, and it will travel continuing through the Milky Way galaxy and circling it about every 200 million years. Now, where is Voyager? So Voyager in the solar system is in the middle of this big sphere. It is just beyond the Kuiper Belt, home of Pluto and other small bodies, but it is far from having left the Oort cloud or this region that we theorize exists and is the home of long period comets. And the reason I go through all of this is because I'd like for you to know that our solar system is almost a light year across, and that Voyager is inside that little blue circle inside of our solar system. And it will be another 39,000 years at 38,000 miles an hour before Voyager leaves our solar system, and it will be more than halfway to reaching our nearest neighbor star at that point. Now, it'll be long since run out of fuel, but it will continue to carry the representation of humans. And so it's very important that we continue this debate until we find true evidence of the Oort cloud. Now, if we move to Hubble quickly, there are three people who are critical to this great instrument: Lyman Spitzer, Nancy Roman, and Edwin Hubble. Obviously, Edwin Hubble, the astronomer, gets credit for finding that the universe is expanding. And Nancy Roman is the mother of the Hubble Space Telescope. She was in a position of chief of astronomy at NASA at the time that this idea began to bear fruit, and she shepherded it all the way through to its completion. And you'll see that Lyman Spitzer wrote a paper in the 40s that outlined the benefits of putting a telescope in space. And you heard me talk about momentarily the effect of the atmosphere on our ability to see at these higher resolutions. And this telescope in space avoided all of those effects of our atmosphere. Ultimately, NASA was funded the same year that Voyager launched. Congress funded the Hubble Space Telescope, calling it the Large Space Telescope at that time. And it was a very important step. Ultimately, Hubble was completed in 1985, and it was designed to be delivered to orbit by the space shuttle. And because of the disaster that occurred during that time, it was not until 1990 that Hubble was delivered and launched. And so now, some 28 years later, we are there. It's important to also note that the National Academy of Science has always been a fan of this set of projects, and in each decadal survey, they have promoted the idea of this observation from space capability as being critical to our work in astrophysics and astronomy. Now, the telescope is unique of all the satellites that have been placed in space by humans. And it is that it is a spacecraft that has been built to be improved. And over the years that Hubble has been in operation, it has been visited 5 times to improve on the original telescope. And for those of you who are a little bit on in years, you probably remember the humiliation of the first few months of Hubble to find that it had a spherical aberration. It's kind of like an astigmatism where your eyes see things, but they're fuzzy all around. And so the first mission going to Hubble was to fix this spherical aberration. And that's what we did in 1993, gave Hubble some new cameras, as well as fix this spherical aberration of the large mirror. And then we went back, and each successive trip, we did something that improved the seeing capability of Hubble. Sometimes those trips required us to make repairs, to keep Hubble healthy, but the main objective each trip was to put new technology on the telescope. And one of the things that you can take away from this list are the abilities for Hubble to improve its sensitivity, to see fainter and fainter objects as we appear into the heavens. And the ability to see these fainter objects allows us to be the incredible time machine that Hubble has become. In the early days of astronomy, these big reflecting telescopes on the ground could see about 6 billion light years back in time, or 6 billion years back in time, or distance of 6 billion light years. As Hubble was introduced, and after its first corrective optics were installed, Hubble was able to push that a bit further back to about 2 billion years after the Big Bang. And there's a red line here that is the redshift number, and it's typically noted as a Z. And this redshift means that, well, let me back up. If you can think about an ambulance or fire truck going by with a siren, and the siren coming towards you, no singers here, as it goes away, it goes, Everybody agree? Okay, that's the Doppler shift of this wave. And this same phenomena occurs with light. As the light is approaching us, it gets bluer. If the light is moving away from us, it gets redder, or red shifting. And so as we see objects further and further back in time, their light has been shifted from visible or higher energy to longer wavelength, lower energy light. And so if you see these new capabilities being added to Hubble, think pushing the frontier of how far back in time we can see. And I will use this Z term from 1 to 20 to talk about this time machine capability of Hubble during our discussion. And so tonight, I thought rather than talk to you about the items in the brochure, I would give you the science brochure and let you see each of the things that the experts over the last few years think are really important. But I thought I would talk to you about this perspective that I have. From my friend Kevin, his poem says, "Climb the rugged mountain, find a flower there. Probe the deepest ocean, see the creatures stare. Magnify the atom, tell what parts there be. Gaze into the heavens, God knows what you will see." And for me, this favorite image is of a dying star. It's the Cat's Eye Nebula, and you see this by looking at this, we find that the star has been dying for thousands of years, and every 1,500 years or so, it puffs out a new layer, kind of like building an onion from inside. And over the last 1,000 years or so, there's just been a recent twist, in this inner core expansion of the star. And so this is a fate of many, many stars, and we find these planetary nebula, called the planetary nebula because early astronomers thought they were planets. So they gave them these names, they called them planetary objects. And so let's see what we can find by peering into the heavens this evening. My first trip is to another dying star. In 1987, an astronomer was standing on the observatory hilltop looking at the sky with his naked eye, and he saw this bright light that was in the sky that he had not seen there before, and he was wondering, what is this? And so he went back in, looked in the Large Magellanic Cloud, and saw this supernova. And it was in the midst of this explosion. Now it's 1,600 years later because it's that far away, but it's a new experience for us. And in the last 400 years, this is the supernova observation of our time. And over the years of Hubble, we've seen this light grow in this ring, and it's a very interesting structure of these two stacked rings around, and we call it an hourglass or supernova 1987. And I've always found it interesting as years have gone by, we can still see the activity of this supernova. Now this is kind of the precursor to either the formation of a black hole or a neutron star, as this mass collapses back and creates a very dense object. Now, the different kind of star observation, if you go back a couple of thousand years, this Omega Centauri was a star in the eyes of the astronomers. And if you remember this angular resolution, they could only see this as a single bright spot. As the years of introducing telescopes moved forward, scientists could begin to peer at Omega Centauri and see that it was much more fuzzy than the other stars in the sky and probably a more complex structure. And so it got to be around the 1700s, a nebula. Maybe like one of these planetary nebulas, but something different about it than a planetary nebula. And then in the 1800s, Herschel identified that it was a cluster of stars, that there were actually some 10 or 20 stars in this clump that we were actually seeing. Now Hubble went a little bit further and realized that there were many stars in this cluster. As Hubble got better, we looked at this and we see not 10 or 20, but 10 million stars. In fact, we're only looking at a tiny speck of Omega Centauri's core, and we see 50,000 stars before you. The other thing that these observations did is allowed the scientists to see how the stars are moving around this crowded area. And as the stars are moving around this clump, it became evident that there is a core here, there's a center, and that center is probably a black hole. So now we have a black hole at the center of this clump. The stars are orderly moving around it. It's beginning to be the definition of a galaxy. But this black hole isn't as big as black holes that are usually in galaxies that we see. So we have this intermediate black hole, which is a rare find, and we have this really tight weave of stars around it. So somehow, maybe the Milky Way galaxy stripped its stars, its outer stars from it, and we're left with these. Now we have this array of different kinds of stars, but they're all old stars. 10, 12 billion year old stars, much older than our sun. And so we look at these stars and we begin to look closely at them. There are these yellow-white stars like ours that's fusing hydrogen. And then there are these blue stars that are kind of different. They're actually these giants that are nearing the end of their life. Now, these stars are really close together, like a third of a light year, 1/12 the distance between us and our nearest neighbor. And as they get close to each other, these old blue in this picture, these red giants do this little piracy, and they steal gas from neighboring stars. And as they steal this gas, they begin to brighten up, and they glow for millions more years, and they get this new lease on life. So these old blue stragglers kind of kick around the neighborhood and suck the life out of all that come nearby. And so I just find Omega Centauri as being this really exciting place that holds wonder for us all. Looking at these star-forming regions closer is the Orion Nebula. And if you go out on a clear night here, you'll see the constellation Orion, and you'll know them by the sword in the air and the straight belt of 3 stars across the waist. Just below the belt is this star-forming region called the Orion Nebula. And in the Orion Nebula are these new stars being born. And these stars, as they are being born, they form up a disk of gas and dust. And in this disk, this protoplanetary disk, we get the formation of young planets. And this is kind of a fertile zone that we know that these large solar systems are being formed. And I'll go to another part of the sky to look at one of these disks. This is the Fomalhaut star in the southern sky, and the star has been blocked out by an occultation disk in the observatory, and around it, the disk of dust has been illuminated by the star. And so we can see this orbiting disk of dust. We can also see from a series of images from 2004 to 2012 the position of this planet, Fomalhaut b. And so Hubble was able to observe over these observations the actual movement of a planet around another star. And this is the first time that we have observed another world directly. We have lots of evidence of planets around thousands of stars so far, but this is the first observation of a planet around a star. Now, this planet has an orbit that's elliptical, as you see, traveling some 4 billion to 27 billion miles away from its star. So it's an interesting place, not exactly one that we would like to live in. In fact, you might say this is what our solar system was like 4 billion years ago. A star surrounded by lots of gas and dust, planets forming up, beginning to clear and collect and gather that gas and dust to become larger or stronger planets. And one of those in our solar system is our big brother, Jupiter. And the news that I'll share this evening about Jupiter is that the great red spot over the life of Hubble has been observed to be shrinking. In the early days of the 90s, the great red spot was about 3 Earths across. And now it's just about 1 Earth across. And there's an interesting bit of research to try to understand, these cyclones are big heat pumps. And they exchange heat from lower levels of the atmosphere, or in our case, the surface of the Earth, up to the upper atmosphere. And so we speculate that there is some other source, other mechanism that is stealing heat from this region and distributing it up to the outer atmosphere, allowing the storm to reduce in size. Now, at the outer edge, and I have to pause here, because if you ever want to get in on the gossip, just a heck of a debate about my favorite little planet here. Is it a planet, or is it a dwarf, or is it a, whatever? And so that debate is raging, and if any of you in the audience have a vote, I'm asking you to vote for Pluto to be reinstated, and we just have lots of new planets to learn about. But Pluto is a good example of this growing capability of Hubble. It's always been observed by Hubble from its very earliest observation. So here you see Hubble with its limited capability of sharply focusing on things, and we see versus a ground-based observatory, we see that Hubble can distinguish Pluto and its largest moon, Charon. We see the ability to observe that and determine what the orbit is of Pluto and Charon. After its first servicing mission with the corrective optics, now Hubble has the ability to see some detail. If you look in the lower left corner, you'll see this bright spot around the equator, near the equator. So that tells you that there's something shiny on the surface of Pluto. And that's not true of Charon. And so it's more of a rougher surface, and it'll be some time before we figure out if all of that's true or means anything. But then we get a new capability on Hubble to see even more detail, and now we can see significant surface roughness on some parts of the planet and smooth, bright spots on other parts of the planet. And then lastly, just before the New Horizons mission to fly by Pluto, we begin to peer in again at Pluto, and we discover it's not a planet, 5 moons in its system. Well, it's an interesting debate. Let the debate continue until it gets to the right answer. And so here we see Pluto and its 5 moons, thanks to the capability of Hubble. And one of the tasks in these observations was to look beyond Pluto and make sure that there were no obstacles for this little spacecraft as it flies into this zone of activity. So leaving our solar system, leaving our galaxy, Hubble pointed at the Andromeda galaxy, our near neighbor. In about 4 billion years, we and Andromeda will be one. There will be this mad dance of these 2 big galaxies. Hubble spent considerable time, and you'll see the little blue box here. So Hubble takes a picture, took 423 pointings to take this swath of the Andromeda galaxy. But it is the largest observation by Hubble, gives us a great deal of insight about our nearest neighbor, about our neighbor galaxy. Our neighbor large galaxy, not the nearest neighbor, but our large galaxy. And so coming on behind Hubble is this telescope WFIRST. And it has some new capabilities. Remember we talked about this time machine being able to peer back in time? It's going to be infrared, so it will be able to see things that are fainter and farther. It will improve on our ability to see the whole sky very quickly. And it's a survey telescope, so WFIRST will give us an entire sky survey so we can look at the distribution of stars in the sky. So there's a search for Earth-like planets or exoplanets around other stars. WFIRST will have the capability of hiding the star and looking around it in lots of cases simultaneously. It will also have the capability of doing this survey of matter distribution so that we can begin to see dark matter, see the presence of dark matter. We haven't figured out how to see it yet in the electromagnetic spectrum, but we'll be able to see this presence of dark matter and the influence of dark energy as we look across the sky. Use the capabilities of gravitational lensing. Oh, there's a term we haven't gotten to yet. and we will be able to do this large sky survey. So hopefully in the 2020s, we will be able to launch W first. Now, what is this gravitational lensing that we were talking about? So normally Hubble is peering at this distant object, straight line of sight. But if you look and you encounter this cluster of galaxies, this is a massive object now, and it is a cluster of not only galaxies of stars, but it's a cluster of galaxies held together by dark matter. And we know that there's some force, some gravitational pull that's holding galaxies together that would otherwise be flying apart. And so we label that dark matter. And so if you look at the light that's being bent by this cluster, as Einstein predicted almost over 100 years ago now, we can see the influence of this lens that's the size of a massive cluster of galaxies. And this lensing shows us this distant galaxy that is seen here in this illustration. And so I wanted to kind of move quickly to what is the example of us using this gravitational lensing. So when we peer at this particular galaxy cluster, astronomers were looking for a supernova, and they were studying the supernova using the gravitational lensing. And this spot in 2011 looked like this. There was a supernova up in the upper corner, that bright dot. And then coming back in 2016, we see this new light. And as we observe this new light and perform spectral analysis on it, we realize that it is the current record holder for the farthest star, single star, ever being observed. In order to observe this star, it took a little sequence of events. First, we have to be observing through a gravitational lens to be able to pick up the faint light from the star. And then we had to have the star being passed by another star, so there was an additional magnifying effect of the second micro-lensing effect of a star that's near it to enhance the light of that star. And so for this moment, we are getting the light of that star amplified about 600 times by these gravitational lensing effects. And so here I present to you the current record holder, Icarus, the star that I show before you. And so for the young folks in the audience, we always talk about things that we know where we were when we first heard about them. Where were you when you first heard that we could observe gravitational waves? If you were here tonight, that's fantastic. It may be your career being a gravitational wave astronomer. It is a new branch of astronomy where the laser interferometer for gravitational wave observations detected this chirp from this collision of two neutron stars. And as these two neutron stars merge, they created this gravitational wave that rippled across the universe at the speed of light. And as it was detected, Fermi, another telescope that watches the sky, detected the gamma rays from this massive collision. And as it turned to point, it told all these observatories around the world where it was going to be pointing and looking for this collision. And over the next 2 weeks, astronomers all over the world using different capabilities observed this collision of these two neutron stars. Hubble captured this observation about 9 days after the collision occurred. And so this is the first time that we have had the organization of a gravitational wave detector listening to the universe for the chirp from two massive objects colliding, producing a significant gravitational wave that ripples across the universe, followed by observations of that event by electromagnetic observing telescopes, gamma ray, X-ray, and infrared and visible light. And we see the image here by Hubble. So, in the annals of Hubble, one of the great observations is to allow humans to see further back in time than we've ever been able to see. First, the Hubble Deep Field in 1995 allowed us to see back to a Z of about 4, and that's about a billion years after the Big Bang. And then the image that's before you in 1997 with new eyes, new capabilities, new infrared capability, we could see this light that is no longer available in the visible spectrum, but is seen in the infrared spectrum. And this is pushing us back now about 800 million years after the Big Bang for these Z numbers that are in the 7 to 12 Z range. And so what we saw in this image in 1997 was about 10,000 galaxies. In the earlier image, we saw about 1,500. So as scientists continue to study these galaxies, we realize something about this distribution of galaxies. And that is that we're only seeing about 10% of the galaxies in this image. And so that means that the cameras that we've built and loaded on Hubble run out of capability because of the faintness of some of these galaxies. And so there's more mass than we had originally thought we were observing, and that additional mass represents another quantum of galaxies. And so you think about what this means. When we first started talking about the ultra-deep field, the estimate was about 150 to 200 billion galaxies in the universe. And now that number is treated as a trillion plus galaxies in the universe. And so if you think back to that Andromeda picture, these kinds of galaxies, Andromeda, typically have 100 billion stars. And we know from these observations of exoplanets that in a galaxy, there are more planets than there are stars. So in the Milky Way galaxy, there are more than 100 billion planets. Some like Jupiter, many like Earth. In addition, there are 1 trillion Milky Way galaxies across the face of the universe. It is just a very neat thing to ponder about our world. And so one of those galaxies in one of these surveys taken by Hubble has pushed us to the absolute limits of Hubble's observing capability. And so you remember these Z's, and all the numbers crunch up in the corner. Z11, or GNZ11, is a galaxy that Hubble has observed. It is the current record holder, and probably will be the oldest galaxy that Hubble will observe at about 13.4 billion years old. And so this is about 1/20th the size of the Milky Way galaxy is today. It has 1% of the stars, but what we know from looking at it is that it is a forming, rapidly growing galaxy that foretells this kind of creation that produces a galaxy with tens of billions of stars. Now, W first will improve our ability to find galaxy candidates like this in this time frame. So we may have an opportunity in the next few decades to push this back further with the help of W first and James Webb. Last month, the European Space Agency released an observation for Gaia. It's an observatory that is mapping all the stars in the Milky Way galaxy. And just in our neighborhood of about 300 light years, they have mapped and located 1.7 billion stars of the 100 billion stars in the Milky Way galaxy. Just in our little suburb outside of the center of the Milky Way galaxy, we have this new mapping. And so it's helping us to understand this distribution of star production across the life of a galaxy. So this is the ultra-deep field simulating a fly-through. And we use this video often to illustrate this, not only the movement through time and space, but also the fact that our universe, these are all galaxies, is expanding in every direction at an accelerating rate. And Adam Rees and his team at Space Telescope Science Institute received the Nobel Prize in 2011 for their discovery with this ultra-deep field in the 90s, that the universe was not only expanding as Hubble thought, but is accelerating in its expansion. Their continued work with this data has revealed that not only is it expanding, but as they improve on the constant that Hubble and Einstein debated in their time, that estimate of the accelerating rate of the universe is increasing. And so we have this rapidly expanding universe, this population of galaxies increasing, and the rate at which star production is occurring continues to defy many of our estimates. And so this next tool that we look forward to adding to the toolkit is the James Webb Space Telescope, and it will help us push the Z factor into the zone of 20, much closer to this dark period where the first light from stars is occurring, the first formation of galaxies is happening. So we will break these records that have been set by Hubble, because James Webb is an infrared telescope. It's allowing us to see this light that has been severely stretched, not just near infrared, but middle to far infrared wavelengths. We will look at stars with the capability to see in detail this protoplanetary disk, and we will be able to see this formation of young planets. And then lastly, we will be able to taste the atmospheres of these planets and search for those right ingredients that make it an interesting opportunity for life. Because one of the things that NASA is always asking is, are we alone? Will anyone find Voyager and read and play its 33 1/3 record that has been included on Voyager? And so this is the 28th anniversary of Hubble, and so I wanted to show you the Lagoon Nebula, which is the image of this year. It is a sighting that looks into this nebula's core, and as we look into the nebula, we see a region that has been buffeted by the winds of these young stars. And you'll notice one of these stars is particularly brighter, but it's masked by dust just in the foreground at the center of the image. But when you look at it in the infrared, you see so many more stars, but you also see this massive star that's much brighter. It is about 200,000 times brighter than our star, the sun. But it is a different kind of star. It is a young star, about 1 million years old, and it is burning fast. It is burning very rapidly through its fuel, and in about 5 million years, it will be gone. It will be probably a brown dwarf. And so some 4 light years across, it is an exciting region for the birth of new stars. And so I want to kind of close with this question of how's Hubble doing. I want to report that Hubble is doing fantastic. It is really healthy. In terms of anomalies, there are few, but they are all within this range of expected for a 30-year-old. And so it is really doing quite well. It continues to be the cornerstone of astrophysics, the astrophysics program at NASA, and it has unique capabilities that are not on the drawing board for the next few generations of telescopes. So we look forward to Hubble serving in its role for quite a while. It's really productive. As I showed you just a few of the recent discoveries and records that have been set by Hubble, it continues to produce a flood of scientific research and citations and references in other research. And Hubble is particularly efficient at the things that it was designed to do, and as it moves into its next position of supporting James Webb and WFIRST and other observatories, Hubble is ready to play this role of a complementary telescope. And so with that, I'd like to say thank you for your time, and you can learn lots about Hubble at nasa.gov/Hubble, or you can follow us on Twitter. Can't say that, I guess, right?